So UFO development is one of the major areas our ops team is focusing on. We are complementing the JEDI core team focusing on developing UFO, including QC, bias corrections for specific ops types. So we are take advantage of the generic framework and also anything relevant to ops space and its usage now is also managed by our ops core team. In addition, we are also working with the relevant pieces to the data ingest, like data conversion, naming convention, etc. And we are also working on validating data impacts and performing scientific assessment. Together, we are also developing diagnostic tools and FSOI tools. So you can see I listed 90 members from our ops core team. And also we have a lot of contributors. Now I only listed the contributors from last year. And they are coming from different organizations like NOAA, NASA, NRL, NCAR, and UK Met Office, etc. So today we are focusing on ops, and tomorrow there's another lecture. So there are a total of 5 lectures dedicated to UFO. All are given by our ops core team members. My talk will be a general overview of UFO, including what are available, how we validate our results, and some common operators. Next talk will be dedicated to the CRTM, which UFO has interfaced to use it as an operator for radiance data simulation. And then the following three talks will have a lot of details, configurations, and examples for you to try UFO at different levels. You could use that as a user, as a developer, and of course, there's a lot of coding involved in those lectures. So there are a lot of lectures talking about the concept of data simulation, which will help a lot to understand the roles of observations play. I just borrowed a slide from European Center's training class to explain this. So you can see that basically what we are doing in data simulation is to combine an estimate of atmosphere state with observations. And of course, we would like to consider the uncertainties for both fields so that we can get optimal analysis. So the final results we call analysis here. Usually the background or the model state estimate, we call the background. It comes from a short range forecast for NWP. But you can also use climatology, for example, for longer term study. So the two kinds of informations are combined. And as I said, the final state is the analysis. So what we are interested in is how we can use observations in such a system. No matter what the simulation is, the analysis can be simplified as background here, and with a correction. And here, the K here is determine the weights that we put to the observation and also the background information. So you can see here, this is analysis, this is background, Y is observations, and H is what we are going to talk today, the forward observation operator. So in fact, sometimes it's only called observation operator. So basically when the operator doesn't involve the forward or background in time. But but the forward operator is more general, including all the possibilities. So let's take a simple example here for 2D field. So we have background in the model grays, and we have observations sparsely located like this. So we want to combine the two information together. The first thing we want to do is to convert the model space variables into observation space. So you can see here, once we have the background using the forward operator to convert it, into the op space, and showing here like a blue dots, then we can compare the observation with the background, converted background. So forward operator could be an interpolation as shown here, but it also could as complicated as a radiative transfer models. For 4D-WAR forward operator, H also involved the forecast model, which forward the background to the observation window or exact observation time, depending on how you want to use that. Some usable terms you probably have heard already. I just want to mention that for once. O minus B, this is the difference between observation and background, and usually we call it innovations. O minus A, this is analysis departures between the observations and the analysis. A minus B, we usually call it analysis increments. H of X, you will see this term a lot in JEDI, because this actually just represents H of X here, and that it's described observational equivalent computed using the forward operator. So this will be my last slide for any general introduction, but I want to mention when you develop UFO, what pieces you will need. So I actually come into the coming gain matrix I mentioned earlier. This can be estimated using ensemble, using optimal interpolations or variational methods. So for example, that for variational system, and you know JEDI actually can have different solvers, ensemble solvers or variational solvers. So for that purpose, for UFO development, you need to consider all the possibilities. So for variational system, K actually can be achieved by solving this cost function. And the components here, this is gradient of J. So if this is minimized, you can get analysis. So the components shown here are the ones we needed for UFO. So R is observational error matrix. H again is the forward operator. The H in bold, it is linearized forward operator. We call the tangent linear operator. Transpose of H is called adjoint operator. And the Y again is observation. And the B, I forgot to mention, but we are not using that for UFO, but this is needed for the, for the solver of the, when you use doing the minimization for the dissimulation, you need this. This is background error matrix. So these components are the ones you need when you develop UFO. Yannick already showed, how important UFO to us. We want to share observations and duplicate, reduce duplication. We want to make faster use of observation systems. And important, we would like to have a community app store so that we can easily share, switch on and off for our data simulation or other data studies. So UFO doesn't read model state as mentioned yesterday. We are actually using this standard interfaces, and we are reader in field values. So what this means? So let me back off a little bit and decompose H first to see what that means. So H could include a few steps if we really decompose the H. So you can see the forecast model first. If we need that, like in 4D-WAR, we can forward the background first to the observation time or time window. And then we can have horizontal interpolation. So this horizontal interpolation will inflate the model's profiles horizontally to latitude and longitude or any other XY coordinates of the specific observations. So here, this is the field values we receive at the UFO level. So we call those as geowalls. And then the first two steps are actually handled by JEDI model and provide the geowalls through the model interface. So they are not happening on the UFO. In fact, only the last steps, including vertical interpolation or other, the variable transforms will happen over the UFO side. So if you look at the simplified figure here, it shows that the observation profile for bending angle, and particularly for this red dot here, showing we need GeoWiles for this red dot. So the model actually interpolate a profile TP in pressure to this latitude and longitude. And then UFO actually using this profile and calculate bending angle at this point. So this is the GeoWiles profiles in this simplified problem. So UFO including forward operator, tangent linear adjoint code, filters, which perform the quantity control, thinning, and of course there are actions attached to that. You can rejecting observation based on certain criteria, inflated errors, etc. Bias correction is the algorithm itself is handled over whoops level, but you can define the predictors on the UFO, and of course there are variable transforms, and everything is controlled by YAML file. So yesterday we already touched some of the YAML file examples, and here is just a snapshot that for each part you can control the configurations through YAML files. The latest code release, including UFO version 1.1, which emphasizes the HFX, bias correction, and QC, validated for NSAP JEDI the operational systems. So here is the list of instruments we have validated. And then we also have example configurations for you to use. So you can see we have all the operational instruments and the platforms. The blue font indicate the platforms right now using at NSAP EMC, and they are the ones we are validating right now. And including, they are covered pretty much everything over NSAP. So using the same input and GeoWiles and observations, UFO can fully replicate GSI using the generic framework. By the way, GSI is the NSAP JEDI forward operator system. So itself is also a variational data simulation system. So we have a very good, actually fully replicate results for most regions except MHS. We are still, MHS, we have the QC and the BC, but we are just trying to minimize the difference. We have fully replicated in SSRO, radio occultation measurements. And for other instruments, we have quite reasonable matching results, and with known regions, there's still something we would like to try to fill in the gaps. We are also developing diagnostic tools to help us. Here it just shows some examples for GPSRO validations. You can see we compare observation with the reference system, which is GSI here. And we are following same things for other applications. We compare ops versus JEDI, and then we see the difference. And difference is really, really small. And there are different metrics we are using to evaluate our forward operators. So today and tomorrow, you actually will see a lot of configurations coming from our GFS, JEDI GFS validations. That's why you will see they are all using the background from FA3. However, FA3 or NOAA JEDI's capabilities are only the first one we are focusing on. We actually also have other systems, model forecast models, and the data simulation capabilities coming in, and then we are monitoring that. So we are going to launch different applications, like what we have done for the JEDI JEDIs, and we are going to validate our UFO for different applications in the coming month. Just a quick example to show why we want to look at different capabilities. And in fact, the generic framework give us flexibility to switch between operators and QC procedures. So here, this example, we actually have the original scheme from our reference system for the surface pressure simulation. And then UKMAN office also have their own way to do that. Right now, this is also available inside UFO. So before we try anything, we want to see whether the the available capability is good enough. In fact, we found out this UKMAN office scheme is better than what we plan to have. So we could just forget this one and just go ahead taking advantage from our partners' development. And this is what we did. That's why sometimes you don't need to have full 100 duplication. You actually could advance your performance already by taking advantage of the UFO. So all the development and validations follow agile approach. So the order of the practical session you are going to follow actually follow the same order for our development and validation. I'll give very brief introduction for that. And in the future, if you are going to develop a new UFO, and those protocol should be followed as well, because this is also following our test protocols. So first, forward operator tangent linear adjoint should be validated without any QCBC. You can use pre-generated GeoWall files following the UDA formats and observation files. You don't need anything from upstream. So using that, it can be validated with reference. Here is an example to show the JEDI actually has the internal function to let you compare with a reference system. And this here reference vector coming from GSI h of x. So this value should come from your ops files already. And also you can have the linear operator, adjoint operator test directly if you run the right command. I believe we have more talking about the different tests in this academy. But this just show you that actually JEDI have provided a lot of testing capabilities. So you don't need to, for any C test, unit test, there's some capability already for you to take advantage of. Similarly, you can do BC and QC, and you can clean up every development by having the separation concern philosophy from JEDI. And of course, for best correction, besides GeoWalls, you also need the best correction coefficients. And doing QC, you follow the similar steps. Eventually, we can go up. We can use the original observation files and the GeoWalls coming from the JEDI interface rather than using the separate files. And you can also have additional processing using UFO capabilities like thinning. We don't have the super orbing yet, but we are developing that. So anything related to the upstream, you can include that in your final test. And of course, everything can should having further diagnostics to help you to diagnose your results. So all the code and examples can be found inside UFO repository. I would like to point out the two important directories you may refer. This one is a source code directory, and this one is test input. So in this source directory, you will see everything related to photo operator. And some of them doesn't refer to any specific observation types. They are the generic operators can be used, especially to the variables. You don't need to have the variable transformed. And there's some directory shows in SSRO, for example, it related to the specific one, and you already have a more complicated operator. CRTM actually has its own repository. So in here, you will see the interface to CRTM. But you have to have the CRTM separately. And also there's a filters, including filters QC thinning, and predictors, which is for bus correction predictors. For any example YAML files, you can find under test input. The C-test YAML you can find from here. They are usually the small test using the small files and give you quick results. When you run JEDI, you will see a lot of C-test, thousands of C-tests, right? So for UFO part, they are here. Of course, for other pieces, they are on the different repository. And there are two references directories here. They are the ones we validated using JEDI administrator. So you can see the more complete configurations following the known JEDI's implementations. Okay, just a brief review on the common operators we have. So here it shows the generic operators we use for the JEDI's applications. Vertical interp we use for many conventional data. It is a linear vertical interpolation for the upper air observations. This is for layer vertical interpolation. So actually you have top and bottom pressure values from observations, then you can have the integration within the layer. And this is being used by ozone, like a total column ozone, or even the ozone layer profiles is still is an integrated layered retrievals. GSI surface model, this is also an interpolation scheme, but this is for near surface variables. So we do have some special treatment. And since we are following GSI implementation, right now it has GSI name in there. However, we are hoping to change that name and make it more generic in the, down the road. So you can see that some YAML examples are listed here as well. The last one is for surface pressure correction. This is more about terrain height correction when you simulate surface pressure. Right now, as I mentioned, we have UKMAN obvious scheme I showed earlier, and there's also another scheme which is following the WolfDA implementation, and you can choose using YAML file. Readings, I'm not going to talk about that really. Ben is having extensive talk for CRTM. So, but just for reference that, we do need horizontal, vertical interpolations, but, we already handled either from JEDI interface or, inside the interface of the UFO. And then the CRTM will provide what we need for from the model state variables, to the simulations. And we actually also have interface to RTTOF. However, RTTOF is only available for RTTOF registered users. So they are not fully public. So just example to show, and you will see this figure probably later, that for each implementations, we actually look at the original reference system, for example, GSI here. And we are trying to follow implementations for each box, QC, or ops inflation schemes. We follow each box and have either generic filters or ops functions follow to combine them and implemented functionality of those blue box. So the code has been refactored, and we are able to represent what we have learned from the reference system here. And you can see for this case, they are pretty much the same. So this is the last operator I'm going to mention. And those, the operator I mentioned are pretty much what we use for the JEDI's validations. So this one is showing the gene SSRO. We actually have more operators for you to use. We have operator for reflectivity. We have two 1D bending angle operator. One is following NSAP JEDI's implementation. One is using the RLPP package. RLPP package is managed by ROMSAF, and it is only available to RLPP registered users. It does have 1D bending angle operator here. And also I listed example YAML files you may find. And also using an RPP package, we can also have 2D retracing operator. So we have been taking advantage of those capabilities. And here is an example we use in our observation monitoring. And this is only a small section of the YAML file. And you can see we can actually run 2 operators and using, different QC or same QC, you can configure them. And then we can run the operators to look at them and compare them. So here, this example from our near real-time observation monitoring. This is back in February, and you can see that the red shows the NSAP 1D bending angle simulation. Blue shows the RLPP 1D, and the green shows the RLPP 2D. And we are actually having active project working on comparing operators as well. So here it shows the formula, the reflectivity. We also have options to define different constants. They are slightly different, but it does have a difference in different opercenters for the constants. 1D operator following this integration, and A is the impact parameter, and the bending angle showing actually is the how much the signal path has been bent. 2D operator, basically you try to simulate the trajectory of the signals, and then you can calculate the bending angle if you know the initial and the final redirections. So 2D bending angle actually simulates trajectory in the 2D occultation plane. So this is just a simplified figure to show why we have different operators for GNSSRO. All right, so my introduction is really simplified version for each of them. If you want to know more about each operator, you probably have to go inside the code to see what's there, what the variables they are using, what you need to have it run. But on the other hand, you can see they are following a very similar framework. So if you want to develop a new operator, just choose an example in the UFO, and there's generic interface you need to follow. And I believe we have lectures talking about that later today. So some UFO is actively being developed, and we are trying to incorporating both research and operational capabilities. And some of them have been validated by our core team, as I showed the examples. So, and also we'd like to mention that all the UFO has been gone through unit test, and also we are trying to follow the protocols we are having. And we are encouraging our collaborators, so everybody who would like to use the UFO follow the protocol as well. Now we are working more on the upstream data conversion, ingest development, and of course, we need to develop more tools for the scientific validation.